All right, is everybody back? Can you hear me? Okay, all right, so let's begin. So now what I want to do is I want to talk about calculating electric potentials. And so we're going to start with the simple case, with discrete point charges. So let me take a look at the following problem. I have 2 point charges located along the x-axis. One is at the origin, and this is negatively charged. And the other one is right here, positively charged. This is x equals minus a. We want to determine the electric field, the electric potential at point P up here, at some location y above the x-axis. I want to derive the expression for V, and really this is fairly straightforward because for a point charge, we use K over R. We're going to say that this is negative and this is positive. And that this Q here is just some positive number, the minus and the negative. Okay. All right. So it's additive. The potential due to this point charge at this point is given by that expression. That's it. Okay. Oh, it's negative. And then for the other one, the distance from this point here to point P, I need to use the Pythagorean theorem, so it's going to be the square root of y squared plus a squared. I'm done. That's it. That's the equation for the potential. And if you have numbers, you can plug in numbers. That's it. That's all you need to do. What if I wanted to calculate the electric field at this point? If I wanted to figure out the electric field at this point, I would need to know how V varies with Y and how V varies with X. So I have to make this more general and then take derivatives. So let me write this in a more general form. And now E is minus the gradient of V. And let's not worry about the Z direction. Let's pretend we're in the 2 dimensions as well. Anyway, the Z component is 0. Because V doesn't change in the X direction. In the Z direction. So then this is going to be So I need to take the derivative of this with respect to x. This whole thing. This one has no x term in it, so the derivative with respect to x is 0, but then this one has a term. And then the y term. And if I want to know the value of the electric field when x equals a, then I got to evaluate this at x equals a. Okay, so let's take derivatives. If I take the derivative of this with respect to x, what am I going to get? K, Q, does that look okay? Check my math. I take the derivative minus the derivative with respect to x. And then let's look at the other term. I'm worried about it. Anyway, let's take the derivative. If I take the derivative of this one, I have a minus sign, a minus sign. And then when I take the derivative, I'm going to get another minus sign. And this one. You can evaluate x equals 1. Okay. I'm concerned about the sign of this one. Hold on a second. Actually, this x that I have to put here is actually the distance. So the distance is a. We're okay. Questions on that? I calculated a v, which was easy. The hard part is calculating the derivative because it requires a lot of work. Now, there's another way to do this, right? I can use the equation in chapter 23 that I used to calculate the electric field. So that would be
Professor?
Yeah.
I don't know if you said this, but essentially all the x's become negative a's, right?
Yeah.
Okay. After you've done the derivative and all.
Yeah, the only
derivative.
You're right. And the only problem I have, and I said something earlier, is that this is minus x squared. Because the vector, the vector, or the potential, the vector r, has a component like this. So it has this vector has a negative x component.
So essentially, so the x squared would then just become a's, right?
Yeah,
or a squared.
A's.
But on the top, it would make that one negative, then both the k, q, x on top one's negative, right? Because the x would be a negative a?
Yes.
Okay, alright.
Oh, I made a mistake. Sorry, that's a y.
Oh, okay.
Sorry about that. Other questions? So that's it. And so I'm only doing one example. This is, I talked about the case where we have three charges earlier. Calculating electric potential for discrete charge distributions is pretty straightforward. The hard one is the case where you have a continuous charge distribution. Sorry, just the camera. When you have a continuous charge distribution, then it becomes a little bit more challenging. And so we want to spend a little bit of time doing this. Well, suppose I have some arbitrary distribution of charge, meaning that I can't. It's an uncountable number of charges, and I want to determine the electric potential here. I have to break up my system into a bunch of PQs, and I have to know this distance. And so I got to write an expression PV. Integrate it. So I got to break up my object into a bunch of little PQs, find the PV for each of the PQs, and integrate it. This is easier because I don't have to find R hat. It's not a vector. It's just a scalar. And so the process is a little bit shorter because I just need to figure out this expression and this expression, put it together, and then integrate. So when I'm doing this, I'm really using the expression for a point charge. I'm breaking this up into a bunch of small point charges and then integrating over each of the small point charges. So I can still assume then, as long as this is finite in size, I can still assume then that the V is 0 at infinity. This method will not work if I have something that's very large, like an infinite plane. And the reason why is because I have an infinite amount of charge. How can I define V to be 0 at infinity? Okay, so really, this really only works for finite size charge distribution. And so I just need to find a dq and an r, and that's it. Remember, r is the magnitude of the vector that goes from the source to the point in question. So in order for us to do these problems, again, and I have this algorithm for doing the calculations. First, choose your coordinate system. You write an expression for dq. Determine r. And integrate. And then check your answer to make sure it makes sense. And again, this is only valid for finite charge distributions, not very large disk or anything like that. Because we define V to be 0 at infinity. So I want to calculate the electric potential as a function of Z for a uniformly charged disk that has total charge Q and radius A, where Z is the height above the plane of the circle. Okay, I want to calculate this. The ring is actually very easy to do. I'm not doing the ring. The ring basically doesn't have to do a uniformly charged ring. Let's do this. Let me draw a picture. I'll do the best I can. I'll draw my yes. That's my disc. It has radius A. We want to determine the field at point P. This is C above the plane. And I want to, how am I going to break up my disk? I want to break it up into pieces so that anywhere around the disk, E is the same. I'm sorry, V is the same. This is uniformly charged. I can break this up into a bunch of rings. Of radius R. And thickness dr. All right, if you have a charge distribution with a disk, you break it up into rings, and you're able to cut that ring out with a pair of scissors. The thickness is dr, the circumference, the length is 2 pi r, so dA, length times width, is that. So that's the area of this blue thing. Okay. dA is 2 pi r dr. dq is sigma dA. Sigma times 2 pi r dr. And I can calculate sigma because I know the total charge is Q. I know that sigma is uniform. So Q over the area of the disk is my charge density. You actually integrate from 0 to A, you'll get Q. Now, what about R? Is the distance, this big R, is basically this little r squared plus my z squared in this square root. So then my dq my dv is k dq over r is k, and this thing once I have that set up, then really I got to integrate over all the rings that make up that disk.
Shouldn't that then be a uppercase R under the dv? So K dq over capital R?
Yes. Thank you. And I have I'm mistaken. Oh no, we're fine. All right, so I have to integrate this. I'm going to pull out some of these constants. And I'm going to use some source to integrate. I'm not going to spend my time here using integration techniques. Okay. You can do U sub. When you do U sub and you integrate, you get that V ends up being 2 Q over A squared square root of Z squared plus A squared minus the upper value of Z. Okay. That has to be, and that's the value sign. When you do the integration, you'll see it's something that happens. You'll see the calculus. And then you can look at the case when Z is much greater than A. This will look like a point charge, and you will get a field. You will get the potential due to a point charge. You have to expand this out, and you'll actually get an expression for the potential due to a point charge. Okay, if you look far away. So you can look at limiting cases. And you can look at the game from real close. Actually, that one becomes a little bit harder because the range is big. Now, this thing has symmetry. So if you're above or below the plane, the electric potential has to have the same value. Okay. If you're above or below the plane, you have the same charge distribution, and so it's going to have the same electric potential. Okay. What happens if A goes to infinity while we have the same charge density? Well, then Q goes to infinity, and we really actually can't use this method of calculating the electric potential. Because this definition assumes there's a point charge. Okay. This assumes the electric potential with the point charge. And if you have something that's infinitely large, we can't use this expression. There's another expression we can use to calculate B, and I'm going to show you that in a little bit. If you want to, you can calculate the electric potential, the electric field at this point by taking the derivative of the potential with respect to Z. The other components will be zero. We've established that already. And so if you took the derivative of this with respect to Z, you would get the electric field of this. And we know that the electric field up here is going to be the Z direction. You might ask, can I do this problem if I'm off the axis? And my answer is, yeah, you can set it up, but you won't be able to integrate it. Okay. You won't get what I mean by that is you won't be able to get an analytic solution. You have to use a computer to actually calculate it. What happens if sigma is not uniform? Well, if sigma is not uniform, it's going to be part of your sigma is going to be part of the integral. You won't be able to pull out your charge density from the integration. And you've done this kind of problem before with the electric field. So I'm gonna blow this picture up. Because the charge distribution is symmetric, this is what the electric potential looks like on both sides of the disk. Whether you're above or below the disk, the electric potential has to have the same form. Notice that the electric potential is continuous at the boundary. On both sides of the disk, the electric potential has to be the same. That function has to be continuous. Why? Because the electric field is the derivative of the electric potential. If you have an electric potential that's not continuous, then you won't be able to take the derivative. You essentially have an infinite field, which is non-physical. So the electric potential has to be continuous as you go from one side of the disk to the other. And that's true in general. Electric potential in general has to be continuous over any boundary. Otherwise, the electric field cannot be calculated. You get something non-physical. Now, the electric field looks like that. The electric field is discontinuous at the boundary, and that's okay. And the reason why is because you have a charge on the surface. When you have a charge on the surface, the electric field is not continuous. And it's okay that it's not continuous. Okay, because the derivative of the electric field is really not related to anything physical that we know of. Okay. So the electric field can be discontinuous at a boundary, but the electric potential cannot be discontinuous over a boundary. And in fact, it switches signs on the other side of the disk. So that second graph is just the derivative minus the derivative of the first graph. And that's what it looks like. Okay. Now let's do another calculation. This problem should be familiar to you because I did something similar to this with the electric field. Suppose we have a line of charge along the x-axis, and it has a non-uniform charge distribution. And I want to calculate the electric potential at point P that you see, point P that you see in the figure. So let me draw my charge distribution. And my coordinates first. Well, I'm choosing the coordinates the right way. The rod. Point P. A, and this is L. Then what I have to do is break this up. That's my little dq, it's a distance x from my axis. And so my dq is lambda dx. We've done this one before. Is lambda naught x dx. We can figure out lambda naught Why? Because we know that the total charge over the entire length of the rod is known. We know that the total charge is Q, so I can solve for this. So that gives us lambda naught. It's 2Q over L squared. If you remember, go review the video with the electric field problem. I did the same thing. Now, what's our R? Well, R is this distance, so it's going to be L plus A minus X. So then dt, okay, dq, then all I got to do is integrate over the length of the rod. And I am not going to sit here and bore you with the integration technique. And when you evaluate the integral, you get the following. I'm sure you can see that here. That's V. If now you write this in general as a function of x, you can take the derivative minus the derivative of this to get the electric field, and you should get the same answer as what we got a couple of weeks ago when we talked about electric field for the system. That would be good for you to practice on. That's a good practice problem. Okay? Take this, take the derivative of this. Well, first of all, write this in general as a function of x. Take the derivative of this with respect to x, or minus the derivative with respect to x. Substitute a back in, and then compare to the electric field you had in the problem you did the other day. And we can do the same thing. What happens when you're really far away? Well, when you're really far away, it looks like a point charge. And then you should take Q over A, to let A be real big, and potential should be Q over A. And again, in order for you to do this, you have to extend this out in series. These are all fun things you can practice with. Okay. To verify that, this look like a point charge is really far away. In other words, A is much bigger than 5. Questions on this? Let me give you another way to calculate V. Without assuming, without using the equation for a point charge. We define the electric potential in the following way. Actually, the electric potential difference. We define the electric potential difference as this integral. And I use that integral to calculate the electric potential due to a point charge. Well, I can do this for any charge distribution as long as I know what the electric field looks like for the charge distribution. I just integrate the electric field. And so this is another way for us to calculate electric fields, electric potentials. The only thing here is that this integral gives you a delta V. If I want to use this to find a V at a location, then I have to know V at one of the two locations. So this, I integrate from A to B. This gives me V sub B and V sub A. If I want to know what this value is, I have to know V sub A. Okay? If I want to know V sub A, I have to know V sub B. I have to specify one of them somehow. And this method works in any case. Okay, this method works in any case. The only thing is we have to know E ahead of time. This is very important if you have a charge distribution that's not infinitely extensive. An example, a line of charge. You can't use the integral K B Q over R for a long line of charge. However, you can use this for a long line of charge. Or infinite plane. Okay, so this works in every case. And it is related to the work done per unit charge in moving the charge between 2 points in space. You also got to remember that I have to know one of these two values to find the other. Okay, so I want to calculate the electric potential due to a uniformly charged insulating sphere. Okay, so let me draw a uniformly charged insulating sphere. So this is an insulator. Actually, if I do the conductor, it's easier. So let me draw it right. Let's say the total charge on it is Q. The radius is R. I want to find electric field outside, everywhere outside the sphere, and every electric field everywhere inside. And it actually works best if I use this method. If I want to find the electric potential out here, at some point in space, due to this charge distribution, I have to know the electric field out here. What's the electric field outside the sphere?
0.
Well, it's not zero, right? It's like having a point charge. This acts like, once you're outside the sphere, it acts like a point charge. I could use Gauss's law to evaluate, to find the field at this point, but I know that this acts like a point charge. It's no different than finding the field at this point due to this charge. The same thing, because of the symmetry of this field. So E is K Q over R squared R hat. And guess what? I'm just going to get the electric potential due to a point charge when I'm outside the sphere. I did that in the first part of our lecture. So then, delta Z minus the integral, okay, Q over R squared, R hat dot yaw. And it doesn't matter how I integrate, what path I choose, but I do know that only the component along this direction contributes to the integral. And I'm going to go from A to B. And I'm going to always choose R hat as pointing outward. And I'm going to make my limits of integration tell me which way I'm going. And you'll see what I mean. So this is going to be B sub B, that's B sub A. I'm going to choose. Now I want to find the electric potential here. I want to choose a judicious point for A. So I'm going to integrate from infinity to R. Oh, there's too many R's here, so I'm going to put now I want to find the potential this is R away, an arbitrary this is R away, so I've got to be careful with my notation. And at infinity, this is 0, because I defined it as 0 at infinity, this is a finite charge distribution. And so when we get B sub B, which is B sub R, I'll move up here. So B sub R is at the so outside the sphere, the electric potential just take Q over R. So let me erase this. The electric potential has to be continuous over the surface. So when you're on the surface, the potential has to be KQ over big R. Now, we need to find the field inside. That's the only way we find the electric potential. We want to go inside. Notice how I did this. I integrated from here to here. I made R hat point outward. My limits of integration tell me which direction I'm moving. You always let the R hat point outward. You let these be parallel to each other. That way you have to deal with minus signs. Otherwise, it gets very confusing for students. Okay, so now what I want to do is I want to find the electric potential somewhere inside there. But the E is defined differently inside, so I have to use a different equation for E. I have to find the electric field inside the sphere. Like this integration, this expression, or this is valid over the region which E is defined. So E is defined differently inside here. We've done that problem. Okay, the last problem I did in the chapter 24 homework, in chapter 24, was the field of the uniformly charged sphere. And this is also in your book. The field of the uniformly charged sphere looks like this. Okay. The field inside the sphere has this function. How do I prove that? What do I use to prove that? Well, I use Gauss's law. If I want to use Gauss's law, I can do this. Okay. And I'm trying to save time. I don't want to go through this again. I don't know if you remember the problem we did last week with the solid sphere and the conductor on the outside. At one point, I actually calculated the expression for electric field inside. Okay. I don't want to do it again.
I remember doing that.
Okay, so I'm just writing it down. So now what I'm going to do is say, okay, the electric field looks like this. And so delta V eventually I'm going to stop doing this. The result is always going to be the same. This dot product is going to give me dr. But you're only going to get a contribution in the hat direction. Okay, so. Let's think about the limits. This is going to give me that expression. I want to know the electric potential at some arbitrary location R. So let's make this R. Let's make this an R. Now, if I'm going to figure this out exactly what this is, I need to know what the electric potential is at location A. So I got to find a location where I know the electric potential. There is a location for which I know the electric potential on either side of the sphere, and that's on the surface. Because the electric potential has to be continuous on the surface, V on the surface is K Q over big R. That has to be the case. So my limit is going to go from big R to little r. And V at big R is KQ over big R. Since I know that, then I can solve for this.
You have to change the R's inside of the thing to primes?
Yes.
R primes.
Good catch. Okay. That's a good catch. And so then I have this little r minus KQ over big R. Oh, I forgot something. minus. Okay, so this is an easy integral because the integral of r is r squared over 2, right? And so let me put this, I'm running out of space, so I'm going to do a substitution here. And so then v sub r, then moves to the other side. Anywhere inside the sphere is given by the following. It depends quadratically on position. If the electric field is linear, then the potential has to be quadratic, so it's going to be 1 power higher because it involves an integral. Okay? Now I can rearrange this expression. I got to erase all this stuff.
Hey, Professor.
Yes.
When did we find v sub big R?
How do we find it?
Yeah.
I'm using the fact that the electric field has to be continuous over the boundary.
Say that again.
The electric, no, sorry, not electric field. The electric potential has to be continuous over the boundary.
Okay.
So that means that whether you're on this side of the sphere or the other side of the sphere, V has to be the same on that surface.
Okay.
And so
All right.
that means I know the field, I know the potential here because I know the potential on the outer surface.
Okay. All right.
Okay?
Thank you.
Okay, so let me rewrite that. I can collect some terms. And I'll do it quick. I can rewrite it in that form. Because this second term is positive, but a 1/2 and a 1 gives you 3/2. So what does that look like? Let me expand this. This is what the electric potential looks like inside and outside the sphere. Inside the sphere, it goes as an upside down parabola. Outside the sphere, it goes as 1 over r. And the function is continuous over the boundary, it has to be. If we say that the potential is V naught at r equals 0, then it's going to be 2/3 of its value on the surface. And you can see that. Let's take a look at the equation again. If you put r equals 0 here, you get at r equals 0, so r is But on the surface, so it's gone down by a factor of 2/3. The magnitude has. Okay, the magnitude has gone down by a factor of 2/3. Okay. Let's do another one. Let's calculate the potential, electric potential, between two long concentric cylindrical conducting shells. The shells have an equal but opposite charge. I can't use the integral k d2 over r because this is infinitely long. I'm going to draw two views of this. So these pretending they're infinitely long. Okay. So the inside is negatively charged. Outside is positively charged. So center view, other view of this. So there's two concentric shells. This shows you one view, and this is from the side, this is from the end. So the outer radius is B. The inner radius is A. I want to know the electric potential in between. I want to know the potential at some point R on the surface. So let's talk about the electric field everywhere. There's actually a homework problem in chapter 24 regarding this. These are conductors. What's the electric field inside the inner conductor? They're hollow, right? They're just hollowed out. So what's the electric field inside? How would I figure that out? Well, I use Gauss's law. How much charge is inside that purple sphere? Anybody? There's no charge inside. So since there's no charge inside here, Gauss's law will tell you that the electric field inside is zero. What about outside? The big sphere, the big cylinder.
Wouldn't that also be zero because it's still a shell?
Yeah. Outside it's still got to be zero.
Yeah. Also, the R shouldn't it be between A and B? Not greater than or equal to B.
You mean here?
Yeah. Because B is the outer and A is the inner.
Yeah, I want to know the field here, and I know the field here, but I'll do this one.
Oh,
I'll do this
okay,
one
that's
next.
right.
In between, the field lines are going to look like this. The electric field will not be zero. Because if I use Gauss's law, I have total charge of lambda times L inside there. Okay? And so if I use Gauss's law, and I'm going to use a cylinder, all right, I got to use a cylinder. And now, so that means I'm going to use that. That Q enclosed is going to be minus lambda naught times L. The normal to this, the normal points outward, the normal this way, but the electric field is inward. So this dot product is going to be the L's cancel. And remember, Gauss's law only allows you to find the magnitude of the electric field. So that's the electric field. We can write it like this. Oops. I don't know why I have a random out there, sorry. This is the electric field. This is the magnitude of the electric field. If I wanted to write it as a vector, the electric field actually points radially inward. Like that. It points in the negative r hat direction, because r hat always points outward. Okay, so now I know the electric field in between these 2 points. Now it's just a matter of integrating this between 2 points to figure out the potential here. I just hope that I know the potential either here or here in order to be able to do that. I need to know one of them. Okay? If I know this guy and this guy, if I know the value of this guy and this guy, then I can figure out lambda. Generally, I know this guy and this guy. And you know why? Because the way I would set the potentials, I take a battery, I put one battery here, one end of the battery here, and the end of the battery here, and then that would give me an electric field in between the 2 points. And I know the potential between the batteries that determines with the batteries. So if I know that, then I can calculate lambda. And I can show you that. Okay. So I want to calculate V. Oh, there's two minus signs. They cancel. What are my limits of integration? Well, my final limits are. Where's my initial point? Well, let's assume we know V sub B. Okay, let's assume we know the potential here. Then V sub R is V sub B plus this integral. This integral is easy, it's a logarithm. And I'm done. That's it. This gives me B as a function of R, as long as I know V sub B. If I knew V sub A instead of V sub B, then I can write it as a V sub A also. Normally, I know the potential here, and I know the potential here. That's normal. I normally know that. So suppose I know V sub A and V sub B. Let's integrate between those 2 points. Let's do this between A and B. I know this, and the reason why I know this is because I can use a battery to set up the field. Negative terminal of the battery here, the positive terminal of the battery here. But let's say I have a 1.5 volt battery. Minus sign here, plus sign here, I have a potential difference of 1.5 volts. And so, if I know this, I can solve for lambda if I wanted to. This integral is easy. Then lambda and that's it. So that gives you the magnitude of the charge distribution. Okay? I'm going to talk about one last thing today, and then I'm going to stop. And then on Tuesday, I only have one more thing to talk about. There might be one homework problem. Right? You should be able to do every problem maybe except the one in the homework. After I finish my lecture, so there's actually a lot of applications of these ideas, and a lot of it just depends on how much time I have. So I'm going to do one of them. I want to talk about electric potential of conductors. Suppose I have a conductor. With any old conductor. Let's say it's charged. You know the electric field inside is zero. It has to be. Okay. We also know that the electric field has to be perpendicular to the surface of the conductor. We also know that all the charge has to be on the surface of the conductor. Well, if the electric field is zero here, and the electric potential is the same value everywhere along the surface, and E is minus the gradient of V, that means then that V equal a constant inside conductor surface. If E equals zero, this gradient is zero. Doesn't necessarily mean V is zero, it just means that V doesn't change, right? If you don't have a gradient, that means V doesn't change. Okay? It doesn't vary. This just is reflective of how V varies. And if it doesn't vary, it doesn't mean V is zero, it just means V doesn't change. So inside a conductor, the electric potential is a constant. And on the surface of a conductor is the equal potential. So here's a graph of what V looks like inside and outside. And notice that V is continuous on the surface. Notice how this is a sphere. This is a conducting sphere. Notice how this one is different compared to the uniformly charged insulated sphere. Compare this slide to the uniformly charged insulated sphere that we just did a few minutes ago. V is constant inside. Also as 1 over R outside. Again, compared to the uniformly charged sphere. In the uniformly charged sphere, V was not constant inside. And then the electric field looks like this for the conductor. That's the conductor. A uniformly charged sphere looks like this. Alright, very fast. That's the electric field looks like for a uniformly charged insulated sphere. Compare them. Here's the equipotentials for a charged conductor. Notice how the equipotentials are bend the most near the sharp edges. That's reflective of the fact that the electric field is strongest at that point, at the sharp points of the conductor. you have sharper electrical potential curves. So you have sharper equal potential curves, then the electric field is going to be greater in those regions. Okay, I'm going to stop here. So I want to redo the demo I did last week. So I kind of botched it up. Part of it has to do with the Van de Graaff. So I want to do it again. And I have to move the computer far away because I don't want to blow my computer. You might not hear me very well. And then we'll be done. Thank you for spending 2 minutes with me. Now here's my Van de Graaff. I'm not going to leave my electronic equipment file there. And I showed you this last time. But I really didn't explain it. I just did it kind of as a gee whiz demo. So here's the neon bulb I used last time. And turn this on. The neon bulb lights up. Oh, let me turn the lights up. Just shock myself. You see the neon bulb light up?
Yeah.
Okay. Turn the lights on. Sorry. If I hold the bulb perpendicular to the electric field along the equal potential, the light will not light up, the bulb will not light up. If I hold it like this, the lights off, the light doesn't go on. But if I rotate it so that it points in the direction of the electric field, the light bulb goes on. It's just perpendicular. Oh, not exactly perpendicular. It's just parallel to the electric field. Gives you an idea what the equal potentials do. No delta V, essentially delta V. I'm a little bit too close to it. Now I have a delta V, the bulb goes on. Okay? Now, sorry, I got charged. That hurt. Because when I touch the switch, I'm grounding myself. So that was a shot. And now I'm going to do the shielding demo again. I got to discharge this thing, otherwise it's distracted.
Did you find where it was leaking from last week?
Yeah.
Because it was leaking, yeah.
There's a leakage. There's a problem right here. This conductor, I can use this to connect the two cages together. And so it was leaking a lot over there.
Okay.
I was trying to find an insulator that didn't work. I mean, I couldn't find one. So I'm going to try it again. I did it yesterday, and I got it to work better. But part of it, I kind of boxed it up. So let me connect this to the Van de Graaff. So what I'm going to do is demonstrate how shielding works. Now, I'm going to try to. Let me zoom in on that cage. Oops. And you can all see the three balls, right? There's one in the middle.
Yeah.
I mean, there's one on the inner cage. There's one in
One
between the two
between.
cages, and one on the outside.
Yeah.
And so what I'm going to do is connect the Van de Graaff to the inside cage. And so all the charge will be on the outer surface of the cage. Which means then that this inner ball is not going to experience any field. The middle one will, And so you eventually start bouncing around. The outer one shouldn't, but it does because of the arcing here. Okay? So here we go. It's not working very well again. When I did it yesterday, the one in the middle was just bouncing crazy back and forth. Hold on a second. Try something. Too much arcing. There we go. So the one in the middle is not shielded at all. The one inside is. The one outside is not because, I don't know if you can hear the mic is too far away, but it's arcing because of this thing. I couldn't find an insulator to place in between. You can tell it's charged, but here's my insulator. You get to track it to the insulator. Now, if I connect the inner conductor to the outer conductor, then both conductors become a single conductor. They basically become one conductor. So what will happen is all the charge will end up on the outer surface. And so that object in the middle won't move at all. When I turn this on, the object in the middle doesn't move at all. Because all the charge is going to be on this outer cage. This is shielding. Right, like when you're in a thunderstorm, it's good to be in your car. You're protected because of the metal in your car. Okay? So nothing's happening. Only the outside one is feeling the effect. Okay? That result is the same as if I took the Van de Graaff and connected it just to the outer conductor, the outer cage. Same result. Because all the charge will be on the surface. Once I connect the two conductors together, all the charge will be in the outer surface. I think even my cables are. Okay. But anyway, I want to demonstrate those things to you guys. So thanks for staying over.
I think it worked a little bit better this time too.
And they work better, that's good.